Last week, we mentioned in outline the so-called arithmetization of mathematics and what they were trying to do, and the arithmetization of calculus is one important and interesting aspect of that history, and as a result of it, infinitesimals, as you say, had gone out of the window, and this is why Russell is saying that Weierstrass, by banishing infinitesimals, has at last shown that we live in an unchanging world. I would like you to tell us the history of arithmetization when it applies to calculus, and in particular, how it is that infinitesimals finally went out of the window.
Yeah, well, the unchanging world bit is a bit more complicated, but let's talk about the 19th century.
Yeah.
So in the 19th century, the use of infinitesimals dropped out. Arguably, it wasn't because they had inconsistent properties. It was more to do with problems that were arising in the theory of continuity, which demanded a more sensitive analysis of how quantifiers work. But that's another story, and we can leave that for the time being. What mathematicians in the 19th century discovered, starting with the work of the French mathematician Cauchy, and then finally being completed by the German Weierstrass, was how you could get away without assuming infinitesimals. And the idea is kind of simple. You don't appeal to these things, infinitesimals. You only have ordinary numbers, the ones you know and love, to play with. But what you worry about is what happens in the limit. Okay. So come back to our example of something in motion. You've got some time, the thing's moving, and it's some finite stretch of time. It moves some distance, and you can compute the average by taking the average speed over that interval by taking the distance and dividing by the time. Okay. Now, suppose you make that distance smaller and smaller and smaller and smaller and smaller. You can't actually make it zero, because then you'd have to divide by zero time, and you can't do that. But what you can see is, as that ratio of distance divided by time gets smaller and smaller and smaller, it approaches a limit. What that means is that as the time duration gets closer and closer and closer to zero, it looks as though that ratio is going to approach a particular number. So suppose, for example, that your ratio turns out to be 2 plus a little bit. Okay. Then as the time distance gets shorter and shorter and shorter, the little bit's going to get smaller and smaller and smaller. Okay, and you're never going to get to 2 exactly, but it looks as though it's going to approach 2. And so 2 is what mathematicians call the limit as that distance approaches 0. So you're not worried about what happens at 0, but you're worried about what happens as that interval gets closer and closer and closer to 0, and you take the limit you're approaching as you get closer and closer to 0 as the instantaneous velocity. Okay. And you do find sort of suggestions of this in Newton, to be fair to Newton as well. So if you think of things in terms of limits, you don't have to invoke infinitesimals. And mathematicians were much happier with this procedure, because applying this machinery, you've got much nicer analyses of things like continuity and so on. But as I said, we won't go into that. Okay. How does this relate to Russell's view that things aren't really in motion? That's not quite the right way to put it, although Russell may well have expressed himself like that sometimes. The thought that is not so much that something is not in motion at any instant, but the whole notion of motion being relative to an instant doesn't make any sense at all. So come back to the way that you compute, say, a velocity using limits. To compute the velocity of something at a particular instant, what you've got to do is consider a stretch of time afterwards or before, it doesn't make much difference, and then consider it getting smaller and smaller and smaller and smaller and smaller. So you've got to take into account essentially the behavior at other points, at the what something does at other points than the one you're dealing with. Okay, so velocity becomes essentially relational in a sense. It's not to do with what's going on here and now. It's to do with what goes on at kind of other instants of time very close to that. So it makes no sense to attribute motion at an instant, except in this derivative sense, in which it's a relation between it and other points of time. So there's no such thing as an intrinsic notion of motion. And I think what Russell, when he's careful, points out is the fact that to the extent that Zeno's paradoxes invoke this instantaneous notion of motion, then it goes out the window with this analysis of infinitesimals. Because the notion of motion at an instant really makes no longer sense, except in this derivative sense, in which you consider it to be a relation to all other instances of motion sort of around it. Okay, so that's why Russell said what he said.
Okay. Do you think that there is a tension between this non-intrinsicality of intrinsic velocity or change and a standard way of expressing determinism and in general the relation that there are between states of the universe at different times? Sometimes we are told that once you're given all the positions and velocities of all the particles that there are, you might be able, if the world were deterministic, you should be able to calculate the positions and velocity of the particles at any other time. And isn't this in tension with this non-intrinsicality of velocity?
No, I don't think so, because if you look at a bit of mathematics that predicts something about something in the future, so let's get a concrete example. Suppose you've got an object that's moving, you know where it is now, you know the forces acting on it, and you want to predict where it's going to be 5 minutes' time, okay? That's expressed by a mathematical equation. The mathematical equation will typically be a differential equation, and what that means is that it involves the calculus, infinitesimal calculus, or the kind of the modern version of that, the calculus of limits. But you've got this equation, and then you solve it. What determinism says is if you know where it is now, you know the forces acting on it, then you can predict where it's going to be in 5 minutes' time. And that's because, given the mathematics, you can solve the equation and get the answer. Okay. As long as the mathematics works, that's all you need for determinism. So if your mathematics doesn't invoke infinitesimals or whatever, which contemporary mathematics doesn't, then determinism makes perfectly good sense without that.
Yeah, okay, but can you coherently say that the way the world is now is at this very instant is determined by the way it was some prior instant?
Well, it's determined by that plus the laws of nature. You know, without the laws of nature, there's no determination. I mean, you've got to have something which ties in how things are now with how things are in the future. That's not going to be told you by the instant. That's going to be told you by the laws of nature, right? And the thought is that once you've got the situation concerning the position, the forces, etc., at the instant, and you know the laws of nature, these things expressed by differential equations, then that information is sufficient to tell you what's going to be in the future. So, yeah, you don't need to assume anything about intrinsic You don't need to assume anything about infinitesimals, for example.
Okay, we can go back to